Thank you for the great introduction. I'm glad we're done with the hardest part, which is finding the slides. Okay, so we have a brave group of people who are caffeinated early on Saturday morning. I'm going to talk about AI in healthcare and the work that we've been doing. To preface a little bit, we do a lot of work in different healthcare areas. That includes the stuff shown on the screen. For today, I'm just going to talk about an application in the dermatology space. If you're interested in the other stuff that we're doing, let me see if the pointer is showing up. It is not. So I'm going to try and see if this works here. Right, so that's the pointer. So there's a short URL here I will show you at the end of the talk again. That is a Google Scholar profile where you can look up all of our research publications. So why apply machine learning to healthcare? There's three main ingredients here to make it really attractive. The first is the amount of data that's growing over time. The second is that you can use AI to make some predictions in situations where there are a lack of expertise, and the predictions that you make should lead to some kind of actionable decision. So those are the three main ingredients that make it attractive and useful to apply AI to healthcare. And just in terms of terminology, you're going to hear these words in various contexts. For the most part, they're basically interchangeable, but technically there's a slight difference in what they mean. AI, or artificial intelligence, refers to the general concept of building a machine that exhibits some form of intelligence. Machine learning is a way, an algorithm, a way to train these models using data as opposed to explicitly specifying everything you want the model to be doing. Deep learning is a category of techniques within machine learning that uses these deep neural networks, artificial neural networks, that help to process complex data. So how do we train models? There's four main ingredients, and I'll cover this again and again. But the first ingredient here is what the input is. Usually for deep learning and AI applications, the input is something complex. And by complex, we mean something like text, image, audio, videos, or something else, something complex here. There's some kind of model in the middle, and that model can be various forms of architectures. They tend to be arranged in layers with mathematical functions connecting within the layers and between layers, such that it can compute something that's useful at the very end. At the very end, the thing that's coming out, that's the model output. You have to define what you want the model output to be, whether it's a number, words, or something else. And then the last ingredient over here is the ground truth. The ground truth defines what is the right answer when the model processes some kind of input, when it produces some kind of output. When do you know that is the correct answer? So these are the four main ingredients when you're applying AI to, in general, but specifically for healthcare. So briefly, let's talk a little bit about generative AI. You might have heard that term recently. And generative AI really refers to the fact that you have input as complex as before, but the main difference between what we traditionally do in ML is that the output is also complex. That means the output is also something complex such as images, text, audio, or video. Now, a closer to reality example over here of a AI application, you have an image, in this case of something on the skin. You have a model architecture that's much more complicated than the 3 to 4 layers that you saw before. And there's branches and other things happening within this model. The details aren't as important for the most part, but there is some kind of complicated architecture in the middle. And the output in this case is a binary yes or no answer for malignancy. The ground truth in this case might come from biopsy or it may come from human interpretation of the same image. But this will be one closer to reality example. Now, keep this in mind because I'm going to make it more complicated right in the next slide over here. And let's step through this from left to right one by one. The first part over here is, again, images. However, instead of one single image, you have multiple images that's being processed, as well as, in this case, what we call metadata, which are structured medical history information. The second part over here is a model, but the model is more complicated, but in essence, it's doing the same thing. Each image is going into one of this kind of like complicated architecture you saw in a previous slide, and then the metadata is going into some other kind of transformation mathematical function that processes it, combines it, and that's, in essence, the model. And then the output over here, in this case, we actually have two sets of outputs. One set of output is for 26 conditions plus a other category, a catch-all bucket, and 419 classes over here, which captures all of the possible conditions. This is what we did for this specific example, but the essence over here is that you have this input, model, and an output structure over here. One note on the ground truth. Ground truth can be really difficult to define. Here's one visual example from a different application where every row here is an image, every column over here is a grader, and in this case there are 5 categories represented by the 5 different colors. Now, what you want to see are horizontal bars of colors, a rainbow chart, where it's the uniform bars from top to bottom. What you see is not that. And in fact, for some of these highlighted rows, the first one, for example, you see that that particular row has every single one of those 5 colors. So sometimes you can see significant disagreement between graders, even when they're looking at exactly the same thing. Now, how do you solve that? In this case, the way we solved it, and note that the label space over here for dermatology is a lot broader than just 5 categories. In this case, the way we solved it was actually by having this rating process where graders were assigning their own differential diagnoses, and we have a voting scheme that really crowdsources these labels from these individuals, and that essentially the majority vote captures what most dermatologists in that panel felt like the top differential should have been. And I won't go into the details over here, but in a nutshell, the results that we saw over here were that the model was much better able to reproduce the panel's differential compared to PCPs and MPs in our study, and they were on par with dermatologists. Now, all of these results were in silico. There was a static data set, it was labeled, we ran the model, and we tested to see how well the model was doing. Now, next what we did in terms of our research was to understand if this could be used to actually help clinicians. So what we did was a study where we had PCPs and MPs, 40 individuals in total. The PCPs and MPs were randomized into one of 2 reading orders. The reading orders refer to the case ordering over here. The cases are exactly the same, but the reading modality, whether it's unassisted, sort of natively how they're reading the cases, versus having some kind of AI-based assistance, that's the part that's changing between these 2 colors. So again, what's happening in the study is that it's randomized and people are looking at cases in 1 or 2 conditions, either assisted or unassisted, and then we can see what the difference is in terms of their diagnostic accuracy when they're looking at when they have AI assistance versus not. This is what the AI interface looked like in this particular study. On the left side here, this is the case. Both the assisted and unassisted arms both saw exactly the same left side. On the right side is the essence of the AI assistance, where what we had was a list of these panels over here, and this first panel is blown up a little bit to get a sense of what's in there, and this contains essentially the predicted condition along with the confidence level in the form of these like blue and gray dots. And they can scroll down to get more of these conditions. So this is the AI assistance. And the main result that we saw over here were that these non-specialist clinicians actually got a 10% absolute increase in diagnostic accuracy by having AI assistance. Relatively speaking, that's a 20% boost. So switching gears a little bit. In the previous work that we showed, we used quite a bit of data to train the model, specifically 20,000 cases and 80,000 images. That's quite a good amount. In most cases, you may not have access to that large volumes of data, and in certain cases, it's completely impractical. So how can we speed this up for other researchers? Well, it turns out if you look at these model architectures, because they're arranged in layers, you can try and figure out what the different layers are learning and whether you can speed up that learning process. And in essence, what's happening in these layers is that the earlier layers tend to learn simpler concepts like textures. And as you go up, it starts learning things that start looking more like portions of objects that it's trained to recognize. And so knowing this, what you can actually do is to pre-train these models such that the intermediate layers have already seen enough relevant images that it knows what to do in these layers such that you have a much easier time training just a couple more layers to do the classification task that you're interested in. So we did exactly that. We got a number of data sets. We trained these models. And then we tested what happens if you just train 1 additional layer on top of these, what we call embeddings. And when we do that, we actually see that, and that's the hatched versus the solid bars, where these are either you can train the full model, or you can just train 1 layer on top of the model. And generally, we're seeing that as you increase the amount of data that you have for this final step of the process, you can actually get close to training a full model just by having a single layer on top of all these other predictions. This URL I'll show again, but this URL shows a blog where you can sign up to access some of these embeddings specifically for dermatology applications, but we also have ones for chest X-rays and pathology. So to conclude, AI can seem complex, but if you distill it down to the essentials, it's basically the input, the model, the output, and what you think the ground truth should be. Note that a ground truth does not have to come from the same input modality as your original input that goes into the model. The models can be trained to interpret skin images at almost expert level performance. And if you create AI assistive tooling based on these models, you can actually help increase non-specialist performance in randomized studies. Now, newer AI methods can enable much more efficient ways of developing these AI tools, and we have a few of these things available for researchers to use. With that, I conclude. Thank you so much.